Hey everyone, welcome to the Question Show. Your questions, my answers, as always. Wherever you are across my channel, if a question pops in your brain, just write it down. I'll gather them up and I will answer them here. Now, last week I talked about Astronomy Cast, which is a show, it's kind of the main thing that I'm known for, apart from Universe Today. But if you just hadn't heard about Astronomy Cast, that was a chance to find out about that. This week, I want to remind you that we also do the weekly Space Hangout. So every week I gather together a team of science journalists, and we talk about interesting space news of the week, as well as bringing in lots and lots of special guests. So if you want to see sort of a more diverse crew of space journalists, work at various publications, various universities, various research groups, and me as the moderator and contributor. So check that out. And that's the weekly Space Hangout. I'm sure there'll be a link here at some point. All right, let's get into the questions. Adam Shupp. Hey, Fraser. I was thinking about the difficulty of space travel on super Earths, and I was wondering how massive can a planet be before its gravity makes space travel by chemical rockets physically impossible? You've probably heard this quite a bit, that we happen to live in the most gravity that is feasible for launching rockets. If the Earth's gravity was 10% more strong, then rockets wouldn't work. And that's not actually true. It's just that the power of chemical rockets allow us to launch heavy payloads into space at 1 Earth gravity. But it would still be possible to launch rockets at heavier gravity than that. And there's an interesting table that someone put together. Actually, this one's on Quora. And the gist is, say you wanted to launch 1,000 kilogram payload and you wanted to go into low Earth orbit. Then if you were using various Saturn equivalent rockets, that if you had, say, 1 Earth gravity, you would need one of Saturn's rockets to be able to launch this 1,000 kilogram payload into low Earth orbit. And the total mass of the rocket would be about, say, 50 tons. And about a tenth the power of a Saturn. So it's, if you only want to launch 1,000 kilograms into orbit, it's reasonably possible to do. But if you went up to, say, twice the Earth's gravity, well, you would need more stages on your rocket. You probably need a 4-stage rocket. You would need to have 5 Saturn V engines, and the total mass of your rocket would be about 1,300 tons. And then in theory, you could launch a rocket off of 4 times the Earth's gravity. But in that case, you would need 20,000 engines, and the total mass of your rocket would be 2.8 million tons. So at a certain point, it gets quite ridiculous. In fact, as you get just above 1 Earth gravity, 1.5 Earth gravity, 2 Earth gravity, the amount of resources it would be required would be ludicrous. And I've talked about this in the past, that if we did live in a higher gravity world, say a 2 Earth gravity world, then how we think about launching stuff into space would be totally different. Instead of, say, launching a space station into orbit, we would rely much more on in situ resource utilization. We would rely on gathering resources in space to be able to build things that would support a larger and larger economy in space. You would launch people off of the surface of the super Earth planet. They would get to space, and that's pretty much all you would launch. It's just a couple of people and the spacecraft required to get them to space. And then you'd be pulling in resources, asteroids, comets, that kind of thing in space to build larger and larger facilities. So it'd be more bootstrapping and less just utilizing the stuff on the planet. So it'd be a lot more complicated, require a lot more research and a lot more technology, but it would still be theoretically possible. And I would say, between 2, maximum 2.5 Earth gravity would be sort of the very limit of what would be possible. And then beyond that, you would be kind of stuck on your planet. But it's kind of sad to think about that there could be civilizations out there where they live on a planet with more gravity. The gravity well is so much stronger that they're stuck. And they can see this universe around them, and they know what's going on, but they have no way to get out of their gravity well. Gravity wells really are for suckers at that point. Fugal. Would it be possible for a rival state to shoot down a rocket during launch with an anti-satellite type weapon? For example, would it be possible for China, Russia, USA to shoot down a launch by their rival if they had a sufficient reason? Like the US was about to take control of a particularly valuable asset, so Russia blew up their FTL spacecraft during launch, etc. Sure, yeah. I mean, that's what anti-satellite weaponry is designed for, is to knock out your enemy's satellites with their various capability. So if you've got some kind of Earth observation satellite, surveillance satellite, a communication satellite, if there's going to be an actual start of a conflict and it's no holds barred, then you would immediately launch rockets and destroy every single one of your enemy's space assets as quickly as possible. And that's why we think that some of these satellites are capable of shifting their orbits to make them a little more unpredictable, because in many cases, you know exactly where this satellite is going around and around and around, orbit after orbit after orbit. Now, the question that you asked, though, was, could you destroy them upon launch? And that would be trickier because you wouldn't know the trajectory that the rocket was going to be taking. In general, there are very standard trajectories that you're going to take. But of course, at these incredible speeds, after a while, you're going to be going in an orbit that is very different. But then as soon as you've gone like once around, twice around, then your orbit is very well understood. The math is known. Your enemy can adapt their anti-satellite weaponry and shoot down your spacecraft. And so really at this point, now the fact that Russia has demonstrated, China has done it, India has done it, the US has done it, every spacefaring nation has the ability to knock down anyone else's spacecraft, satellites, space stations, anything. They're all sitting ducks up there. And yeah, if you launched a spacecraft, unless you were just doing a straight shot towards the target, which is often done, like when we launch rockets, say, to Mars, they don't go into orbit around the Earth first. They just go straight to Mars. Or if they're going to go out to Jupiter, Saturn, etc. Those would be harder to chase down and hit. But if you're going to go into orbit around the Earth for a little while, then you're kind of a sitting duck. Bjorn Larson, aren't you ashamed for having advocated the failed SLS Orion fraud during most of the last decade? Is it okay to be wrong sometimes if one finally confesses it to go on righteously hereafter? And I'm not even a Catholic. So I would not say that I have advocated for SLS and Orion. And I think it's really important to distinguish between my job as a journalist, reporting on the things that happened, and my opinion as a space journalist. As a person, I guess, right? So I think, my job as a reporter, as a publisher of Universe Today, is to report on the things that are happening. And so the various things that are happening with the Space Launch System, with Orion, are newsworthy events. Hardware is being completed, tests are being done, budgets are being assigned, astronauts are being chosen, timelines are being developed, etc. And in general, it's our job to report on that as news. And my opinion on the whole situation doesn't really play into it. It's just like, this has happened, let's report on it. On the other hand, of course, I have expressed my opinion many times. And, I've expressed that my opinion is that in general, I think that the space shuttle was a mistake. The Space Launch System is a mistake. And in fact, I'm not a big fan of goals-based space exploration at all. I'm a much bigger fan of a capabilities-driven space exploration. And so what that means is that instead of aiming for some specific target, like going to the moon, going to Mars, you just try to increase your overall capability in space exploration. Better propulsion systems, better materials, longer lasting, farther orbits, and just build up larger and larger capabilities that then can be used for all kinds of things. And, when you look at, say, the budgets that have been used for the various spacecraft, like what it took to get humans on the moon was about $450 billion in inflation adjusted dollars. If you compare that to the amount of budget that it took to fly the space shuttle, it was about $211 billion. So about half the cost to fly the space shuttle compared to do the Apollo program. And the budget so far for the Space Launch System is about $23 billion. So the cost of the Space Launch System compared to the Apollo program is like 1/20th of the cost Now, obviously, each individual launch after that is going to be more expensive and it will add up to the overall budget. But even the Space Launch System with the various Artemis to return humans to the moon is going to end up costing a tenth the budget of the Apollo program, a quarter the budget of the Space Shuttle program. And of course, the exciting contender that's coming up, of course, is Starship, coming from SpaceX. But we've seen right now, as we're recording this in late 2021, we've seen a lot of Starships explode. We've seen one Starship successfully fly to 10 kilometers altitude and then land on its landing pad. Yeah, if Starship works, when Starship works, it'll be a total game changer, and it'll make every other piece of spacecraft hardware irrelevant overnight. But at the same time, as a person that is planning the development of humans' exploration of space at NASA, like, do you sit and wait for Starship to be developed with Elon Musk at the helm, whatever he wants to do? Like, is that now NASA's policy, is whatever Elon Musk wants to build is what NASA does? At a certain point, NASA has to take some agency in what it's doing. And so I think right now, continuing the development of its existing equipment makes sense considering the landscape as it stands right now. You know, if I was in charge of NASA, I wouldn't do it. I would cancel Space Launch System and Orion. But NASA can't control that. The U.S. Congress decides what space hardware is built and that Space Launch System is going to be going to the moon. NASA actually has no control over that. They can try to figure out what the spacecraft is going to kind of look like, but at the end of the day, it has to build Space Launch System. So that's a voting thing. That's a choose different leaders for your country kind of situation, as opposed to an executive decision at NASA. So should I confess? No, I feel like I've been fairly consistent across the entire period of time as I've been talking about this. I've been reporting the news. My opinion is that it's probably all a mistake and we need to shift to new other methodologies of flying. So steady as she goes. Double D. Since time slows down at greater and greater speeds, does time stop at the speed of light? Do photons even experience time at all? I actually did a video about this very concept. It's terrible, but we did it. It's like, do photons experience time? I think was the title of the video. And I was like walking in the forest. We were experimenting with like, can we have me walk across a very sort of bad, rough trail, and the camera was bouncing around. It sucked. So don't watch it. And now you're going to watch it. But yeah, if you take relativity and you punch in the speed of light for the speed that you're going, the amount of time that you experience becomes zero. And what that means is that from the perspective of a photon, they are created and then they fly through space at the speed of light. They experience no time, and then they encounter whatever they're going to encounter. Say they bounce off the retina of your eyeball. And so from a photon's perspective, no time has passed, which is obviously super mind-bending. But they're just photons. So it's not like they think or experience anything. But if we could build a fast as light spaceship, then yeah, you point it at your target, you turn the engine on, you would then be at your destination and you would turn the engine off. And you would have experienced none of the intervening time. And the part that's weird is that if you then put in speeds that are faster than the speed of light into the relativity, then time goes backwards. You get negative time. So if you wanted to travel to Alpha Centauri at faster than the speed of light, you would arrive before you left. And that's just what happens with the equation, which of course is impossible, but that's because it's probably impossible. So yeah, crazy though. Nelson Fernandez, can you see the city lights from the Earth's night side of the moon? Probably not, but really good tests haven't been done. You know, during the Apollo missions, the astronauts wanted to find out. And in fact, when the Apollo astronauts were out at the orbit of the moon, so they asked, could we see the city lights of the Earth from the moon? And so the astronauts took some pictures of the Earth, and they were unable to see the city lights on the moon. Now, part of the problem could be that there was just a lot of clouds in the image. Part of the problem could be the scattering of the atmosphere. And it could just be that the camera optics weren't able to pick that up. And so maybe in the future with like really nice telescopes, you would be able to see the city lights. And also the Apollo astronauts were in the sunlight. The Earth was in the sunlight. And so they were looking at both the sunny side of the Earth and the darkened side of the Earth. And so maybe if the conditions were absolutely perfect, like you were on the moon during a total lunar eclipse, and so the Earth passes in front of the sun and blocks it completely, and you're now in the shadow of the Earth and you're looking at the moon and you've got a good telescope, then maybe you could see the city lights. But still, it's not going to be a very impressive thing. You can see the clouds and the seas and the landforms, but you can't see the city lights at night. But you can definitely see them from Earth orbit. More questions in a second, but first I'd like to thank our patrons: Stephen Reisdorf, Alexandru Vadaman, Paul Kaup, Bill Christian, Scott Bragdon, Wayne Francis, and the rest of our 799 patrons for their generous support. Want our videos early with no ads? Join our community at patreon.com/universetoday. Arjun, can we detect exoplanets we can't see using their magnetic fields? Like, would that be a productive way of finding exojupiters, or would that be a waste of time? Absolutely. In fact, astronomers have already found a handful of planets through their magnetic field. And this is such a great idea. So what happens is, of course, you've got a star, and the star is giving off large flares like the sun, or like really mega flares like a red dwarf that's putting out flares that are like 100,000 times more powerful than the sun does. And as that flare interacts with the magnetosphere around an exoplanet, you get these emissions of radio waves that are coming off of the planet that are essentially telling you that this magnetosphere exists. And astronomers have detected these emissions of radio waves, telling them that there are planets orbiting around the stars. They didn't use the transit method. They didn't use the radial velocity method. They didn't direct image them. They found them by the magnetosphere. And of course, what's really exciting about this is that really we think that you need to have a magnetosphere around a planet to protect any life on that planet from all that radiation from space, the star, but as well as cosmic radiation. And so it's kind of a twofer, right? You're detecting this planet, and you're also essentially detecting a planet that is protecting any life on it from the dangers of space radiation. One of the best ideas to do this is to build a radio observatory on the far side of the moon, something fairly big. We've done a video about this, that would then be very sensitive and capable of detecting these. And in theory, it could be a really powerful way to find targets. You could essentially find planets in the habitable zone around stars, and then you know you've got a planet that is not only in the habitable zone, but is also protected by this planet-wide magnetosphere. There could be life there. Michael West, what is the mission you wish was never cut from a program or canceled? And which one do you think would bring the most important scientific information? I believe I'm very much on record for saying that the mission, say it with me, is the Terrestrial Planet Finder. And this was a mission that was designed to come after the Kepler mission and would have launched somewhere around 2010. And NASA ended up canceling it. But what it was going to be was an interferometer. It was going to be probably 4 identical Kepler-class spacecraft flying information in space. And so this would be, as we've talked about with interferometers in the past, that if you have multiple telescopes that are separated by space, as long as they get their alignment perfect down to 600-ish nanometers, then they can act like a telescope that is the size as the distance between these planets in terms of resolution. And so you would end up having these telescopes flying in space, acting like a 200-meter telescope, 1,000-meter telescope, a 10-kilometer telescope, to be able to resolve and to be able to separate the star from its planets. A lot of the big challenges were, how would you block out the light from the star in order to be able to see the planets beside it? And of course, now new ideas have come up for that. There's star shades and coronagraphs and things like that. But just the idea of having even just a general purpose interferometer, essentially the Very Large Telescope, which is here on Earth, it's 4 8+ meter telescopes, but put that in space and have them be an interferometer where they can change the distance between them depending on the target they're looking at, would be an incredible telescope, something that's more capable than even LUVOIR. So yeah, the Terrestrial Planet Finder was the mission that was canceled. The other one, the ground-based one that I'm really sad was canceled, was the Overwhelmingly Large Telescope. And so when the European Southern Observatory was working on the next generation telescopes that would come after the Very Large Telescope, they said, what's the biggest possible telescope that we could build on Earth? And the answer was 100 meters. And so they called this thing the Overwhelmingly Large Telescope. And in the end, they canceled it because the budget was going to be too high. It was going to be like $1 billion or something. And they went with the less expensive, more feasible, extremely large telescope. And this one is 39 meters across, which is still a ludicrously large telescope. And so if we could have gotten the 100-meter telescope, and who knows, it feels kind of inevitable that after the extremely large, we'll get the overwhelmingly large. That would be incredible. A 100-meter class telescope here on Earth would be just insanely helpful. So those are the two missions that I really wish had worked, but haven't so far. Phil Deshane. Hey Fraser, have you read Robin Hansen's 1998 regarding the Great Filter, which states that we should hope not to find life inside the solar system due to the Great Filter implications? Yeah, absolutely. And in fact, there's been a ton of videos about the Great Filter and the implications of finding life in the solar system. But the gist is, if we want to survive for a long time in the Milky Way as a civilization, we want to hope that we never find life anywhere, ever. And especially not intelligent life, because it means that we're doomed. So the Great Filter are these various kind of goalposts life has to pass on its way to becoming a technological and eventually star-faring civilization. You can imagine a bunch of these, like going from single-celled organism to multicellular organism, or going from animal intelligence to civilization, organization like human beings, and gaining technology and so on. And so many of these filters, you could think of hundreds, that we have already passed them. We already got to multicellular life. We already got to technology. We already got to cities, etc. We already got to spaceflight. And so you can also imagine a bunch of these filters are ahead of us. There's going to be one that is maybe not having nuclear war, not having artificial intelligence destroy everything on Earth, not having a plague, not having a science experiment collapse the Earth into strange matter, etc. And so if we find life on Mars, for example, and we find that there's like single cellular organisms there, multicellular organisms there, then that means that whatever is the Great Filter, whatever is the reason why there are not intelligent civilizations out there, it is not behind us, it's in front of us. And it means that it's just now a matter of time before whatever that filter is, the one where we turn on the super large Hadron Collider and turn the Earth into a black hole, is in our future. And so we don't want to find life, because if we don't find life, then maybe there even isn't a Great Filter. That if we're the only civilization in the universe, then there's no such thing as a Great Filter. And whatever future science fiction you hold in your heart is possible. HQ Cart. Everything is orbiting something. Are galaxies orbiting anything bigger? Yeah, galaxies are orbiting clusters of galaxies. So we live in the local group. And so you've got the Milky Way, you've got Andromeda, you got Triangulum, and then you got a few dozen dwarf galaxies. And they're all buzzing around this collective common center of gravity of the local group. But the local group is part of a much larger structure called the Virgo supercluster. And that is many galaxies, thousands of galaxies, that are all orbiting around a common center of gravity. There's a little bit of a larger structure than that, but that's about it. So you've got, if you look at the large scale structure of the universe, you get up to superclusters, you get these big walls and various interesting shapes, but it doesn't keep going up and up and up. So superclusters are almost the biggest structures that are out there. Raphael Domenichini. Can a star collapse directly into a black hole without a supernova, without ejecting any mass? In theory, yes. And it's seeming more and more likely that this is actually more common than we ever thought. The original idea with a supernova turning into a black hole was that you would always get this core collapse supernova, that runs out of fusion in the core. It burns different elements all the way up to iron. And then when it reaches iron, then it can no longer support fusion in the core and it collapses in on itself, produces a black hole, material bounces out, and you get the supernova. And there's been a few examples now of what were stars that should have created supernovae that are just gone. They just disappeared. And so the thinking now is that, in fact, if the conditions are right, you can have all this infalling material turn into a black hole, and it's so efficient that it doesn't get that supernova ejection event at all. And so it might be that there's a certain amount of mass, or maybe there's a certain amount of like speed that the black hole is rotating and the size of its accretion disk, or maybe if it has some kind of interaction with a binary companion. But it's looking more and more likely that there are some giant stars that when they die, they just wink out. They just collapse in on themselves and disappear, and you're left with the black hole. And this is absolutely on the cutting edge of astronomy at this point, and I wouldn't be surprised if we learn a ton more about these in the coming years, especially as we get incredible observatories like Vera Rubin, which is scanning the sky every couple of nights. They'll be looking for stars that disappeared. And it might just be that we don't see as many supernovae out there as we should because the stars are just imploding, which is amazing. Whiskey Canuck. Do you think that we should move away from huge complex telescope projects to constellations of small and cheap network telescopes? Yes. I think if I was in charge of NASA, which for many reasons, like I'm a Canadian, I can't be in charge of NASA, I would move towards more telescopes that are less powerful than these enormous flagship missions, at least until the capacity for the existing telescopes is fulfilled. Like the Hubble Space Telescope, which is now 30 plus years old, is 2.4 meters across, and it is oversubscribed. It is 10 times oversubscribed. You could launch 10 more Hubble Space Telescopes and still have astronomers waiting in line to be able to use the capabilities of Hubble. And so that means we haven't answered all the questions that Hubble has to answer. There are real advantages to ground-based observatories and to more inexpensive space-based observatories. And I think what we're going to find as Starship starts to fly is that these less expensive telescopes are going to be a lot more feasible to launch. You know, like when you are building a very complicated, very large telescope and the launch costs are so expensive, then you have to just balance. Like if it's going to cost you $500 million to launch your telescope, then you're going to want to build a telescope that is worth $500 million of launch costs. But if the telescope's only going to cost you $1 million to launch, then do you just build $1 million of telescope and you're not really super concerned about how complicated it's going to be? So I think that we're going to see a shift into a lot more telescopes that are less expensive. We're going to see a new generation of telescopes launching on these cheaper launch systems that will provide a lot more coverage in space. Yeah, but I mean, at the same time, there is a limit to what you can do with a smaller telescope. Sometimes bigger is better. And so James Webb is going to be able to answer questions that no other telescope, 10 Hubbles, couldn't answer the questions that James Webb will be able to answer. And so the question is it better to have 10 times as many observations than one super powerful telescope? And I think it's better to have more cheaper telescopes right now until we've fulfilled all the capacity. I find that astronomers, like just scientists, are very clever in using less powerful gear to answer questions. They're able to push these instruments beyond what anyone was expecting they were going to be able to do. And I think having more Hubbles, for example, would just give more people a chance to try these really clever experiments as opposed to waiting in line for James Webb while they wait in line for Hubble. But, that's just me. But I see really cool ideas for telescopes all the time in research journals. We report on them all the time on Universe Today. And it's a thing that really excites me. I would love more experiments and more tests, more cool ideas, and less big monolithic flagship missions. But that's just me. Matt Jono 2, what does it cost for a scientist or institution to use Hubble? It's free. The Hubble Space Telescope is free to use for anybody who puts in a proposal and it's accepted by the Hubble Steering Committee. And that's the key, is that there is a group of people who work with the Hubble Space Telescope who are shuffling all of the proposals based on the amount of observation time they need, the part of the sky they need, are the targets close together, which instruments do they require, how long are they going to need it for, and they're constantly queuing up all of these research projects. And of course, when something really urgent comes up, like there's a new supernova, then Hubble has to be brought in to take a look at that, and that shifts other people down the queue. So it's a very complicated operation. But yeah, it's free to actually use the Hubble Space Telescope. And in fact, there's no limits on where you are. So anyone from any country around the world can use the Hubble Space Telescope for free, which is pretty amazing. All right. Those are all the questions this week. Thank you, everybody who asked them in the YouTube comments, and also all the people who join me for the live show. Remember, I do this show every Monday at 5 p.m. Pacific time. So if you want to hang out with me and other space nerds, come join us Mondays, 5. All right, we'll see you next week. If you want a single comprehensive resource for space news, you want to subscribe to my weekly email newsletter. Every Friday, I send out a magazine of space news with dozens of stories, pictures, brief highlights, and links you can find out more. Go to universetoday.com/newsletter to sign up. It's totally free. And did you know that all my videos are also available in a handy audio podcast format so that you can have the latest episodes as well as special bonus material like interviews with me show up on your audio device? Go to universetoday.com/audio or search for Universe Today on iTunes, Spotify, or wherever you get your podcasts. And I'll put a link in the show notes. Thanks to all the moderators, and a special thanks, as always, to Chad Weber and Nancy Graziano.